On August 12, 2026, the moon crossed directly between Earth and the Sun, turning daylight into a moving shadow. Millions of people watched the sky darken, but one of the most revealing views came from orbit. The International Space Station briefly appeared against the eclipsed Sun, a tiny machine crossing an enormous cosmic alignment. That image is more than a beautiful coincidence. It is a reminder that an eclipse is not an event happening in one place. It is a three-dimensional geometry experiment, written across the Earth, the Moon, the station, and the distant surface of the Sun. Tonight, we will follow the shadow, understand why totality is so rare, and discover what a spacecraft sees when it races through the darkness. Begin with the scale. The Sun is about 400 times wider than the Moon, but it is also about 400 times farther away. That almost perfect ratio is why the Moon can cover the bright disk of the Sun from our viewpoint. The match is temporary on the cosmic calendar. The Moon is slowly moving away from Earth, so total solar eclipses will not remain possible forever. An eclipse starts with a new moon, when the lunar hemisphere facing Earth is dark. Most months, the Moon passes slightly above or below the Sun in the sky because its orbit is tilted by roughly 5 degrees. Only when the orbital paths intersect at just the right time does the Moon cast its shadow across Earth. The shadow has two important parts. The penumbra is the broad outer shadow, where the Moon covers only part of the Sun. Inside it lies the umbra, the narrow core where the entire visible solar disk disappears. The penumbra can stretch across a continent, but the umbra is a fast-moving corridor, often only a few dozen to a few hundred kilometers wide. For an observer inside that corridor, the transformation happens in stages. The first bite taken from the Sun may look harmless. Then the light becomes strangely thin, shadows sharpen, and the temperature begins to fall. Small gaps between leaves project thousands of tiny crescents onto the ground, because every gap becomes a pinhole camera. Near totality, the atmosphere seems to lose its ordinary color. The horizon may glow with a ring of sunset even though the sky overhead is dark. Birds can settle, insects may begin their evening calls, and people often report a physical feeling that is difficult to describe. The world has not simply become darker, but unfamiliar. Then the last fragment of sunlight vanishes. The black disk of the Moon is surrounded by the Sun's corona, a ghostly atmosphere made of superheated plasma shaped by magnetic fields. The corona is normally hidden by the Sun's glare, so totality gives scientists and observers a rare natural mask for studying structures that extend millions of kilometers into space. The bright points around the edge have names that sound almost delicate. Bailey's beads are flashes of sunlight shining through valleys along the Moon's uneven surface. The diamond ring is the final burst of photosphere light beside the dark lunar disk. These moments can last only seconds, but they reveal the topography of a world 250,000 miles away. Now pull back from the ground. The Moon's umbra is not a stationary stain. It races across Earth at thousands of kilometers per hour as the planet rotates beneath the lunar shadow. A person standing still experiences darkness for only a few minutes, because the alignment is moving continuously. The International Space Station sees a different eclipse. At an altitude of roughly 400 kilometers, it travels around Earth at about 28,000 kilometers per hour. The station can cross the path of the Moon's shadow, but its crew does not simply wait for darkness to arrive. Mission planners calculate the position of the station, the Moon, and the shadow down to the second. From orbit, the station can observe the shadow as a dark oval or curved region sweeping over the atmosphere. The boundary is not perfectly sharp because Earth's atmosphere scatters sunlight. Blue light spreads through air, while dust, clouds, and aerosols modify the shape and color of the moving darkness. A spacecraft can also see the eclipse from the side. Instead of looking up at the black moon, an astronaut may see a dark cone extending away from the lunar surface. The cone is created because the Moon blocks sunlight in 3 dimensions. It is not an invisible wall, but a region where direct sunlight has been removed from the geometry of space. That is why an image of the station crossing the Sun is so difficult to capture. The station is moving rapidly, the photographer is on a rotating planet, the Sun is dangerously bright, and the window of alignment may last less than a second. The camera must be ready, the focus precise, and the exposure short enough to freeze both the spacecraft and the solar detail. The station's silhouette can look almost unreal: solar arrays, trusses, radiators, and modules reduced to a tiny black pattern against the sun. Yet every line represents a working system. The arrays gather sunlight for electricity, radiators release waste heat, and the pressurized modules protect astronauts from vacuum and radiation. An eclipse briefly changes the station's environment, but it does not make space safe. The spacecraft still moves through a thin trace of atmosphere, still faces micrometeoroids, and still depends on redundant life support systems. Outside the station, a spacesuit must provide pressure, oxygen, cooling, communication, and protection while the astronaut works in a darkness that may last only minutes. The most important science during an eclipse happens because the sun is not a smooth lamp. Its surface boils with convection, its magnetic field twists through the corona, and violent eruptions can send clouds of charged particles toward Earth. These solar storms can disturb satellites, navigation systems, radio communications, and electrical grids. The corona is especially valuable to study because it is far hotter than the visible surface below it. The sun's photosphere is roughly 5,500 degrees Celsius, while parts of the corona reach millions of degrees. That temperature difference is one of the central puzzles of solar physics, and every eclipse creates a natural opportunity to map the corona's changing shape. Modern scientists do not depend on a single eclipse. Space telescopes use coronagraphs to block the sun artificially, and solar observatories watch the star continuously. But totality still offers a unique combination of scale, resolution, and simplicity. For a few minutes, the sky performs an experiment that no laboratory can reproduce at full size. The August eclipse also reminds us that prediction is a triumph of mathematics. Astronomers can forecast the moon's position, the Earth's rotation, the station's orbit, and the shadow's path years in advance. The prediction depends on gravitational models, laser measurements of the moon, atomic clocks, and careful corrections for the irregular rotation of Earth. Long before modern instruments, eclipses were treated as warnings or supernatural signs. Today, the event is no less emotional, but the explanation has changed. Understanding the mechanism does not shrink the experience. It deepens it, because the darkness becomes evidence that distant worlds obey the same physical rules everywhere. There is also a quiet lesson in the moon's changing distance. The total eclipse is possible because several scales happen to match in our era. In the distant future, the moon will appear too small to cover the sun completely, and totality will be replaced by annular eclipses, where a ring of sunlight remains visible. That future is not a disaster. It is a reminder that the sky is dynamic. Continents move, stars age, orbits evolve, and even the most familiar patterns have a beginning and an end. We happen to live during a narrow chapter when the sun and moon can create a perfect dark disk and a luminous corona above our heads. When the next eclipse arrives, look for more than the spectacle. Watch the shadows under trees. Notice the change in the wind and the color of the horizon. Remember that the darkness is traveling, and that somewhere above the atmosphere, a spacecraft may be racing through the same alignment at orbital speed. The station crossing the sun is a tiny image, but it connects several human ambitions at once. We learned to predict the moon, built a laboratory in orbit, placed cameras between worlds, and turned a moment of darkness into measurements of a star's invisible atmosphere. For a few minutes, Earth stands inside the moon's shadow. From the ground, it feels like the universe has paused. From orbit, the shadow sweeps onward, revealing that nothing has paused at all. The planets continue moving, the station continues falling around Earth, and the sun continues to burn across the distance. That is the real meaning of the eclipse. It is not the disappearance of light, but the revelation of motion, scale, and connection. A dark circle crossing the sun can show us where we are in space, and how extraordinary it is that, for one brief moment, we can see the architecture of the cosmos with our own eyes.